What if you're here? What if you're beyond that? Beyond that, here's what's going to happen. You haven't seen that because I haven't pushed you to kill the transistor. You with me so far? Right. We haven't gone beyond that area. That's a breakdown zone. Just like a diode. We haven't gone to breakdown zones. Does that make sense? We kept our work within a certain operation zone. Because that's where you want to use your transistor. So where do I want to use it? Right here. You can pick any point you want as long as it's right here. Do you agree? Mm-hmm. The points you pick are going to be relevant to what kind of circuit this is. Are you using it as a switch? Are you using it as an amplifier? If it's an amplifier, what kind of amplifier? Does that make sense? Are you using it as a clipper? Are you using it as an oscillator part, as a feedback system? Whatever it is it belongs to, we'll decide where do I want this little doohickey to be. Now, how do I control this line? Well, I have full control over that, over VCC RC. Mm-hmm. That's my external devices, regardless of the transistor. I choose what VCC and RC will be. I get a 2222 or two, and if I want the same load line, it doesn't matter. I can get it. Because that's dictated by the RC and VCC. Does that make sense? Now, if I had RC as a potentiometer, then I can have a load line that can do what? From this point, does what? Does this, because this ratio here will change. VCC stays the same, but RC does what? Goes up or down. Then I can play with a load line. You with me so far? It's where engineering comes in. This is why we do these things, so we can manipulate where we want to be. You with me so far? If I want a transistor to drive a motor and I need a lot of amps, right? So I need this point to be as high as I can go, because that's IC. And if this here happens to be a motor instead, or a motor in series with it, then I want to adjust the potentiometer to get the maximum amount of current there. Do you agree? To give it enough torque to turn. So a robot arm. Then if I want to slow it down, just like add more RC. Does that make sense? That lowers IC. Most of these DC current are controlled by the amount of current you put in. Does that make sense? So how would I control that? Well, that's perfect. I could use a circuit like this. I know my fulcrum is here, and I could put a potentiometer there and just move up if RC goes down, move down if RC goes up. Why? Because IC goes down. Does that make sense? Right, so inverse ratio of RC. RC goes up, IC goes down. And I can control where I want to be. You with me so far? Now, if the manufacturer of that motor says you cannot have a maximum current of 1 amp, well, great. Right? So I know my IC of saturation cannot be at 1 amp. Maybe I'll bring it down by 80%. You with me so far? Down to 80% of 1 amp. That's an operational zone. You look at the specs of the motor, and you say, where would it be happy to operate? Where it's not overheating, where it's okay, given any temperature, random, what temperatures you're working on. You with me so far? This is where engineering comes in. You start looking through specs and say, how do I come up with values? How do I come up with these RCs? Well, it all depends on the environment you're operating this thing in. You're going to start asking questions like, okay, my ambient temperature is 25 Celsius. I'm looking at the spec sheet. It says do not exceed 1 amp. Beyond that, there are no guarantees how that motor will behave. Does that make sense? It will overheat. All right, well, I'm going to be at 0.8. If they say the happy medium at that temperature is 0.8, 0.7 within that range, yeah, good, I'm going to be there. So what would it take for me to get that? Well, I'm going to saturate the transistor to drive the motor all the way. Do you agree? And if I want to throttle the motor back down, I'm going to move my point from saturation to almost cutoff to shut it down. Well, I'm going to do that. Well, I'm going to be controlling with RB because I can control IB. You with me so far? Once I have a set point where the motor is going to be, then I can move IB up and down. IC will move up and down to the max. The potentiometer I would have here, I just set it once to make sure that I end up with this ratio that I want to be, 0.8 amp. Great. Then after that, I will stop playing with this guy to do what? And here's my motor right here. And I can just like play with this and throttle the speed. Is everybody seeing how this works? Right? So thus you have a motor control device right away. Okay? And the beauty about this, you don't need a lot of current here. So your potentiometer will not overheat. It will be nice and it won't spark. Does that make sense? Which you want, because any time where you have hands anywhere, you want as low current as possible. And the base of a transistor offers you that. Where you want the load, the max current, that's at the collector of the transistor. Don't touch that area. Typically, if it's a power transistor, you'll see them. They're beefy, they have fans and so on. I mean by that, metal stuck to it, to dissipate heat. You'll be amazed what's out there. It's not little tiny doohickey you have in your back. If you're controlling motors, that is. Is everybody seeing what I'm doing here? So the point is, you have a lab now. Well, we're going to have to do this load line. So you have to be comfortable with the characteristic of the diode. This is called quadrant 1, by the way. Okay. Quadrant 1, what do we need? Because there are several quadrants in this. This is quadrant 1, 2, 3, and 4. So I don't confuse you. Right? So the ones we're interested in, typically, is this and this. Part 1 of your lab was quadrant 3. Was VBE against IB. Does that make sense? Quadrant 1 is usually VCE versus IC. Once you know these two, you're good to go. Now it's just a matter of how do I put that transistor in the circuit. That means now I can control the load line. I can control IC set max, where it's going to be. I can figure out what my VCE of cutoff will be. That's basically your power supply. Does that make sense? And go from there.
Okay, so you said for the first one is VCE versus IB. What was for the third?
Which one? This one, right here.
Yeah.
This one is, what you're going to end up with is, you're going to end up with this graph that looks like this. This is VBE versus IB. It looks like a diode, just flipped around. Does that make sense? That's what I wanted to see in that part of the lab. And you will see this curve here at what? 0.7 volts.
Oh, for the graph?
Right. At 0.7 volts, it'll just like, boom, just like a diode. It's a junction between the base and the emitter. Does that make sense? Yep.
Is the 0.7 volts the avalanche point?
It's not an avalanche. It's the what do they call it?
The elbow.
Elbow.
Yeah.
Right? I'm trying to think from French to English. It's the elbow. Avalanche is in reverse when we're using the Zener region. Does that make sense? Mm-hmm. Right? So, but then you have to also be worried about what? The power region. Do not go there. That's goodbye. Does that make sense? That's why you have an Imax reverse. IB max. That's why you don't just go trigger happy and put a 1900 volt here. You have a lot of current going through. Is everybody with me so far? Right? This is what we want VB, and you've noticed RBs are usually much higher in scale than RCs. Look at your circuits. You get to see that trend where RBs are hefty. The reason is because they want them to keep the current as low as possible. Does that make sense? Because you're just using the current for control. That's all you're using it for. It's not to drive stuff. Well, yeah, it is because of the fact that it moves up and down, but the real current that's usually connected to the load is IC, or sometimes IE. So far, so good? Okay, good. All right, so we're going to do virtually the lab. Yeah, this is pretty bad. I mean, either I get a really bad pen or something that requires. There you go.
I think it's a bad voice.
Yeah, you see, now what you need to do, folks, is you need to practice these circuits. No excuses. The midterm exam is based on this. Right, and remember, you do it over and over and over until you do it like in your sleep. And the reason I'm saying that is because that's what I had to do. Is that why I'm punishing you?
I think they're cool.
Yeah, maybe. But in the end, you're going to be able to converse with it, troubleshoot, build stuff on the fly. That's where you want to be. Does that make sense? You want to be comfortable with the circuit. You're looking at something, you get your instruments, you stop measuring, boom, boom, you find the errors, you find the problems. It's because you understand the behavior, you understand where it's supposed to be. Time is money. If you're in a QC control or anything like that, you need to know what you're doing. And the only way you're going to know how to do it is you got to do it over and over and over until you go to sleep, you're dreaming circuits. Then I have done my job. Okay? All right, so you need to be there. All right, let's do the lab. I'm surprised I'm still standing.
You get the lights.
Hmm?
You get the lights.
Yeah. So I'm going to... Look, who's in here? Oh, this thing is not on yet. Check this out. Same circuit. This is a good practice circuit. You know it's going to yield results. Does that make sense? Specifically with your 2N3904. Does that make sense? Okay, so it's exactly the same circuit. And, okay, how would I go about this lab? Well, build it. Build it and follow the instructions. There are several parts. One is the way it is, try to figure out these values and beta. That's what we're going to do, part one. Which is a good review for the midterm. Does that make sense? And then we worry about the load line. Load line will not be on the midterm. But it's always a good idea to know how to do it. Does that make sense? All right, so whatever I'm doing now is also a review for the midterm. On top of knowing how to do a diode, bridge rectifier, you need to draw these out of your head. And how to do the ratios for the transformer, N1/N2. Absolutely must do. Okay, and a Zener diode. So I'm going to go and start a new lab. But before that, I'd like a space for it. I'm going to go to session 10, 14, 24. New schematics, file, save as, right away so I don't waste any time. We can call this one lab 3. Okay. Now, remember, you could do lab 3 in the simulator just to get an idea what you're going to be doing. What I want you to do in the lab is to actually do it and measure and do everything. And your paper should be based on a lab, not a simulator anymore. Unless it's a simulator lab. Okay, so I'm going to go ahead and pull out some transistor. I'm going to go ahead and pick an NPN right here. And pick out a couple resistors right here. And then right here. Then pick up, oops, come back here. There you go. Then pick up a couple power supplies. Or one, actually. Right here. Get some wires. Okay? Oops, before I do that, let's get the ground. There we go. Let's get a wire. Okay. We're going to call this one RB. I like to capitalize the B and the C right now. In the future, when we're dealing with AC circuitry, you'll see why we have certain things. And I put a 50K here. By the way, this is a great opportunity to see if we're getting the same result as the quiz, right? 100. This here, I'm going to call it VCC. VCC. I'm going to make 9 volts here. And for the simulation, just DC op for now. Okay. Stick it right here. There you go. What do we have? What did we get on the board before? Well, let me put some points here so you can actually see them. And see. Here. All right, so let's run this again. So VC is 7.36. How much did we get? What we did on the board. See how close we are. The only reason we're not going to be maybe close, it's matters of beta. Does that make sense? Right. What were the values that came up on the board earlier? Well, IB is 163 microamp here, which is not bad. Right. And then I have 16 milliamp, which is really close to 14 milliamp. So we're right on the money. Does that make sense? So if you divide 16 by 0.16, what do you get? Go ahead. 16 divided by 0.16.
Oh, point.
Yeah.
Point 10?
Please divide.
0.01.
16 divided by 0.16. There's 100?
Yeah, that's because you didn't set the transistor, so it just uses.
Oh, this is not our transistor. Remember, very good, because it depends on beta. Does that make sense? So we're going to go over here and we're going to change this to our transistor. 3904. Okay, run it again. There you go. Now we got 46 divided by 0.16. That's because beta is much higher. You with me so far? Huh?
287.
280, yeah. Pretty close. Is everybody on board now? Now understand you can actually predict these things and control them. And definitely VC dropped to 4.3 volts, which was about what we got. Now, that's the beginning, part one. Go to the lab. Part one, based on the circuit below, complete the following procedure and collect data stuff in the following with the following component value and measure IB, IC, VC, VRC, VRB, and beta. Can we do that? Absolutely. Right? Now, part two, reduce RB to 40K, 20K, 10K, 1K, 100 ohm. And then take the same notes. Remeasure all of those IB, IC, VC, VRC, VR, and figure out if beta changed. Is everybody with me so far? So you're going to do it that many times. Some people asked me before, why do we repeat? That's what lab is for. So you can see you have enough data points. If you don't have data points, you have no lab. You with me so far? Right? So let's say you have an AI model. You can't train an AI model on 2 points. You're going to give it a gazillion stuff before it says, okay, well, that looks like a dog. Does that make sense? It's the same thing. So, and then part three, notice go back to 50K, but this time do what? Increase RB and do the same thing. That's it. What do you end up with? Well, you're going to be asked to do what? For each step, collect these, and then for the data analysis, let me just add one more time what I want. Just to be clear, I'm going to do part four. Draw the relationship between IC and VCE based on part 2 and 3. Because you're going to have a whole bunch of ICs going up to a certain point, going back down. Does that make sense? Same thing with VCs. So draw the relationship or graph. Just graph the relationship between IC VCE. That will be the load line. So far, so good?
Mm-hmm. So only make it one graph.
One graph. Yeah.
So putting down parts.
All these parts will help you for that graph. Yeah. So you collect all that data, then I can go back, part one, it showed me up to a certain point. Right? Because here's what's going to happen. Yeah. Come back. Here's what's going to happen. You're going to end up, let's say you're at 50K. At 50K, you ended up here with a specific, with RB at 50K. RB at 50K means you have a specific IB. You with me so far? So I'm here, I have a VCE, and IC when RB at RB equal what? 50 kilo ohm. What's going to happen when I increase or decrease RB? When I'm playing with IB. So that means I'm moving up the line or going down the line. That's all. Does that make sense? So this is my point of reference. I'm going to go below it or above it. and drop each point, which means my ICVCE for the different what? RBs. In other words, my RBs are controlling my IBs, you know? So, let's say I went for a bigger RB. What do you think is going to happen to IB? Then your point is going to be somewhere in here. Do you agree? Then your other point is going to be here. The more you increase RB, the more you decrease IB. In other words, the more you decrease IC. You with me so far? The other way around, as I decrease RB vis-a-vis 50K, I'm going to be increasing IB and hence increasing what? IC. And notice I didn't touch the 100 ohm on the other side, which means this will be my max point anyway. And didn't touch VCC. So I know my cutoff and saturation point. No matter what, I'm going to be between these 2 points. Does that make sense? So I am controlling this circuit with IB by changing RB. And I'm moving the point across the load line. Now what if I wanted the load line somewhere else? Change RC. Does that make sense? With the same power supply, either you move it this way or that way. What if you added more power supply? Well, then you're moving it from under. You with me so far? Yep.
Can we only change RC or can we change VCC as well?
Again, in a circuit you can do pretty much what you want. Right now I need you to keep VCC and RC the same. To just get the load line based on a bunch of changes to RB, basically a bunch of changes to IB. So far so good?
Yeah, to change the load line, change the RC.
If you want to change totally the load line, you change RC. Right. Right. Or VCC and or VCC RC. What if I change VCC and RC? Well, then I can have a load line here. You with me so far? It goes in parallel. What if I just changed RC vis-a-vis where I was? Then you would have something maybe like this as a load line. Especially if RC is big. You with me so far? If you start increasing RC, then your load line will look like this. Because if you increase RC, you're not going to get as much current as a lower RC. What if I decreased RC? Well, then you're going to have a load line that looks like this. Again, starting from this point, if you kept it at the same VCC. What if I increased VCC and decreased RC? Well, then you're going to end up here. It's up to you how you want to design it. You are the designer. You decide where you want that load line to be. That's going to be your key ingredient on how your circuit will operate. The reason is this. Eventually what's going to happen, on that load line, you're going to pick a point for your AC signal to ride. It's going to change that load line up and down. It's going to oscillate it. Now, if your input signal is too big, by the time it gets here, we'll clip it. And by the time it gets here, it will clip. You will remember those clips you saw?
Yeah.
Right, because we've reached cutoff and we reach what? Saturation. Hey, I could use that to create a square wave. Almost. Depends on the frequency. So you can reshape signals if you wanted to. Does that make sense? Hey, I'll put a capacitor or an inductor and play around and see if I can create different kinds of filtering with the signals. It's a whole bunch of things you can do with this. If it's an audio amplifier, I want to make sure my amplifier does not saturate or cut off, otherwise you end up with clipping and you're going to lose data. Does that make sense? The voice, the music is on that information. You're not reshaping signal, you're just amplifying. Is everybody with me so far? Right? Good? Excellent. All right, so this is after next week, after the midterm, after your load line, we're going to start injecting AC signal to see how it behaves within that circuit. What I suggest you do right now is you go to the lab. Or at least sit down and do it where? In the simulator. And it's a good review for your midterm exam. Does that make sense? It's probably one of those days where you need to sit in the corner and look at the corner. And stay away from people. little. Now is the time not to get confused, which means what? Move away, sit somewhere in the corner, and just beat your head against the paper until it sinks in. Are we clear? Okay? Yep.
Yeah, my simulator, did you provide us with one, or are you saying like go online?
Go ahead.
Oh.
Have you been in this class?
No, yeah, sorry, my simulator, I thought you were talking
Right.
about like taking online.
No, there's a flight simulator across the yeah. I actually enjoyed it. It wasn't bad. Yeah.
So to recap, the midterm is based off of diodes, transformers,
And transistor.
Okay.
But load line might not be a component, but understanding how to do a load line helps you with what you're doing. Definitely the operating point where you are. Just like the quiz. Okay? Okay, good. All right, so let me go back through attendance just to make sure I got everybody.